So we're back here to our Lecture 5 Social Interactions directory, and we're going to be looking now at the epidemic model. So I'm going to open that up and fire it up in Bensim. Again, no. Let's look at this model scaled as it is. And so this model is a slightly more sophisticated version of the, again, 3 cohorts, susceptible, infected, and recovered or recuperated stocks that we saw earlier. And let me walk you a little bit of what's been included in this model so you can take a look at it. Let's look at the susceptible. Susceptible population can there's a couple of ways that the susceptibles can go. Susceptibles can get vaccinated, and if they become vaccinated, then they're automatically recovered. So they're, again, they won't, they won't become ill, or they can become ill and infected and become part of that stock. Okay. The infected can become cured. Okay. And so they can just become cured, and then they become recovered, or they can die. Okay, and there's a rate of mortality there. We're going to see those in a second. The recovered occur because infecteds get recovered, because susceptibles get vaccinated. Now the recovered can get, in this model, can get re-exposed to disease, and then they can become susceptible again. And that sort of triggers the cycle again. Let's take a look at some of the variables here. Let's take a look at the susceptibles and what goes out into that. Let me look at the equations. So susceptibles are equal to the exposed minus the ones that become ill minus the vaccinated. Okay, there's an initial value of 900 in this population, and the units are individuals. Okay, individual. If let's look at the possibility of being vaccinated for a susceptible. So the vaccination, it's essentially it's the units of individuals per month, so it's a first order process. So it's a product of the susceptibles times a rate of vaccination. And let's take a look at what this rate of vaccination looks like. The rate of vaccination here, it's a ratio of the people that become ill as a fraction of the susceptibles. Okay, so whatever fraction of susceptibles become ill times the availability of vaccines. Okay, the availability of vaccines is another variable here that is simply it's a non-dimensional factor between 0 and 1, with 0 meaning that there's no vaccines available, and 1 which means all full availability of vaccines. There's no limitation. So here, what this is saying is that 50% of those that can be vaccinated will be vaccinated. Okay, so that works into the rate of vaccination. So that's essentially the story with vaccines. Now, susceptibles can become ill. Okay, in doing so, it's essentially this here is the SIR fraction of the model. The inputs of susceptibles into the infected pool is the product of the susceptibles times the infected times the rate of infection. Okay, so there's this will be the beta rate. This rate of infection is the beta rate that we saw earlier. Okay, that rate of infection, let's take a look at it. It's a constant, and it's equal to 0.001. Okay, in this case. So once they become infected, the infecteds can become recovered through a rate of recovery. Okay, this is what we call the gamma in the SIR model. It's got units of 1 per month, and so if that happens, they can become fully recovered. They can become cured, but they can also die, and there's a rate of mortality here. So the dead are the product of the infected times that rate of mortality. Is a first order process. So this wasn't included. The infected in the SIR model can only be recovered, but they cannot die. In this case, they can. So this is a little bit more involved model. Okay. So the once they, if they're cured, they become recovered. The recovered are fed by the vaccinated, um, and now the recovered can become exposed. Okay, so there's a rate of exposition here, um, which means that they can, reacquire the disease and become susceptible. Okay, so that's how the loop is closed. Oh, here there's a little auxiliary variable to show the, the total population. So, okay. So let's look at the model setup. And if you look at the settings, this model is run from 0 to 20 months, okay, and time steps of 1 month, okay, that's fine. So this is a, the study over a 20-month period. And if you look at the initial values, there's 900 susceptibles to start with. There are 100 infected, so that's, the disease starts with 100 people, and there's 0 recovered. So there's no one's recovered at the initial point. Okay. So with the model setup, you can go and run it. Go to simulate. Runs very quickly, and then we can just start. Graphing, so let's start doing that. Let's see what happens to the susceptibles. Remember, they started at 900. If you look at the graph, the susceptibles start at 900. They drop because they become infected. So they're no longer, become infected. They're no longer susceptible. And then I guess as we'll see the other dynamics, but it seems that the susceptibles start picking up again. So there's got to be some recoveries. Okay, so that's what it appears here. Let's look at the infected. What happens to the infected? And as we saw, essentially there was a peak in the infection. So the starts at 100 and then goes up to nearly 200 and then it starts dropping as people get recovered over the 20-month period. And if you look at the recovered, same story. It starts at 0, but as people start getting recovered, it grows and then it sort of tapers off as the system stabilizes. You can look at the total population and graph it, and you can see that actually the total population started at 1,000. The effect of the disease, of the epidemic in this case, is to make the total population drop to just a little bit over 850 people. So there is that lasting impact of the epidemic in terms of, and we can look at the, number of deaths, and you can see number of deaths are here. So there's about 10 people dead, and then it goes up to 20, and those are, and then then it sort of graphs out until the end. There's very few people dying, but it does add up to the 100 plus people that were lost in the process. Okay. So that's pretty much it for this model of interaction. You can play around with this a little bit. You can one thing you can do here, actually we can try it here on the fly, is to do a graph, and let's define a new graph here. Okay, and we're going to call it epidemic cohorts, something like this, and these here will be susceptible, infected, and recuperated populations. Nice little title. In the x-axis we'll put time, okay, and the minimum for the population for the time would be 0. The maximum will be 20, and that's the range. Let's select the 3 populations here. Let's look at the susceptible. Okay, that's one variable. Let's look at the infected, and let's look at the recovered, or the recuperate. Okay, let's do that. Let's OK out of this, and let's display it. Select it and display it. Okay, so now you see, oops, sorry, here, and I'm going to I'm going to close this and I'm going to zoom on this plot. You can then, let me just zoom, oops, view, zoom, let's zoom, oh, it didn't, for some reason it's not showing, so maybe I can't make this, oh, I can make this bigger. Oh, forget the zoom. Let's forget the zoom and let's make this graph bigger. I like this better. And then you can see here the three, the three that population, the three cohorts, and their dynamics. And this is essentially an interesting case because it shows how three populations or three stocks get exposed to a common phenomenon, and see how it affects the three of them. And you can see, the susceptibles are going down and then recovering, the infected going up and then recovering, or tapering down because of recovery, and the recoveries going up and then stabilizing as well. So that's the interacting dynamics of these three. So I think I'll leave it at that. You can do many more things with this example, and I'll let you play with it. Hopefully you've enjoyed all of these cases, and we'll keep discussing some of these features next week. I'm going to stop this now and go back to the lecture.